So Taylor series can also be used to help us evaluate indeterminate limits. Okay, so at this point, we've seen a lot of different series, infinite series, geometric series, harmonic, alternating, p-series. We've talked about Taylor and Maclaurin series, which are specific power series. And here we have some examples of some frequently used Taylor series, right? So we want to know how we can take that series and what it's going to look like when we write it out. We use it enough that we're familiar with it. And in this next example, we're going to use this e to the x part of the Taylor series. So here we have the limit as x approaches 0 of e to the x minus the quantity 1 plus x divided by x squared. And if we looked at trying to evaluate this limit, we would get e to the 0 minus 1 plus 0 over 0 squared. E to the 0 is 1, minus 1 plus 0 is 1 over 0. We have 0 over 0, which is an indeterminate form. So sometimes if we're dealing with complex expressions that we're trying to find the limit of, and we recognize that, hey, maybe there's a power series, a Taylor series hiding in there, we can use that as well. And this is just a different manipulation. So what I'm going to do is I'm going to take this part, the argument here of our limit, the function that we're trying to find the limit of. I'm going to take that function and write that as 1 over x squared times the quantity e to the x minus the quantity 1 plus x. All right, now one thing I know is I can expand e to the x as a Taylor series polynomial. And what that would look like, I'll leave my 1 over x squared. So that expansion of just e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And that would continue going, right? But we still are eventually going to have that minus 1 plus x. So if we look at what we have here, we can simplify 1 take away 1 and x take away x. I'm going to be left with 1 over x squared over 2 factorial is 2, plus x cubed over 3 factorial, and 3 factorial, 3 times 2 times 1 is 6, plus, we would have x to the 4th over 4 factorial, didn't write the terms on the upper line, x to the 5th over 5 factorial, and it would continue going to some nth term, x to the n over n factorial. But what would happen is we're going to end up with, if I distribute this 1 over x squared, distributing that to all my terms leaves me with 1/2 plus, that would be x cubed over x squared, just gives me x over 6, plus x fourth over x squared is x squared over 4 factorial is 24. 4 times 3 factorial, which is 6, plus x cubed over 5 factorial. And so what we notice then, if I take this polynomial expansion and I write it in up here for my limit, all right, so then what I'm doing is I need to do the limit as x approaches 0 of 1/2 plus x over 6 plus x squared over 24 plus x cubed over 5 factorial plus some x to the n minus 2 power over n factorial. So as we approach that nth term there, well, what ends up happening is I'm plugging in 0, right? If I try to evaluate this and I plug zeros in for all of these, I'm going to always have 0 divided by a number for every term that follows my first term of this series. And all of those 0 terms are going to cancel out. So the limit here is just equal to 1/2. And so that shows us how a Taylor series expansion could be used to help you find a limit of some function that is in indeterminate form.